Oh, test. Hello, everyone, and welcome to this afternoon's session on particle phenomenology. Today, we are very happy to have Professor Gian Giudice. Is that right? Giudice? Professor Giudice. Thank you. We're very glad to have Professor Giudice to speak about his recent work. Professor Giudice is a professor at CERN, and he specializes in the Standard Model and applications of supersymmetry and various other very interesting stuff. So we're very glad to have him to speak about exploring the origin of electroweak braking and the flavor structure after the OHC. Please take it away.
Oh, does it work? Hello? No. It's
Sorry.
no, no. Okay. So so in spite now you can hear me, right? Yes? Okay. In spite of all these searches, nothing unexpected was observed. And the results from the LHC have really radically transformed our understanding of the particle world. And because our expectation was that new phenomena would be within reach of the LHC. So does this lack of new phenomena mean that we have discovered everything that can be discovered? Is a high energy physics program now completed? Well, in spite of the successes of the Standard Model, it would be ridiculous to believe that we have reached the ultimate layer of knowledge. There are too many open questions that aren't addressed by the Standard Model. First, there are issues related to gravity. Gravity can be embedded into the Standard Model by treating general relativity as a low energy effective quantum theory. But as soon as the energy approaches the Planck scale, the effective theory breaks down and it must be replaced by a complete theory of quantum gravity. So what is quantum gravity and how does it link with the Standard Model? Why is a cosmological constant so much smaller than any known scale in physics? Then there are the problems related to cosmology that which cannot be explained in the context of the Standard Model. So is dark matter made of a new kind of particle not included in the standard model, and dark energy is inflation driven by a new particle. Can particle physics account for the observed cosmic baryon asymmetry? Another weakness of the standard model has to do with some structural aspect. It means some features that have no apparent explanation. So why is SU3 times SU2 times SU1 the gauge group? Why there are 3 generations of quarks and leptons? Why is the charge quantized, which in less technical terms, this is a question: why all hadrons have integer electric charges and why atoms are neutral? And then finally, there's another class of standard model problems, and this is related to some unexplained parameters or features. So for some of these problems, we have clues of possible explanations, even if we don't have a definitive proof. So some examples: what determines the value of the gauge couplings? Well, grand unification theories give some indication how to do it, but we don't know if it has the right explanation. Origin of neutrino masses, well, based on symmetry arguments, it seems very plausible that the smallness of neutrino mass is a result of some dimension 5 operator suppressed by some large scale, but we haven't settled the issue. Why is CP violation in strong interaction vanishing or nearly vanishing? And we know that the axion seems the most plausible explanation, and so the experimental search has to continue. But while all these puzzling questions require answers, and the research has to continue, in the following, I want to focus on 2 mysteries of the standard model. One is what is the origin of electroweak breaking, and the other one, what determines the mass and mixing parameters of quarks and leptons. And these 2 mysteries play a central role in the search for new phenomena at future high-energy facilities. So colliders may give important hints also to other problems, in particular to the cosmological ones, but these 2 open problems really provide, for me, the strongest motivation for pursuing research with future high-energy colliders. So because their answer may lie within experimental reach. So let me focus on these 2 issues. Let me start with the problem of the structure of quark and lepton masses. So there are 2 aspects to this question. The first is what I call the flavor puzzle. And this is the question of why quarks and lepton masses and mixings are what they are. And the question is scientifically valid, not only because a final theory should be able to determine all of its free parameters, but also because quarks and leptons show a very specific pattern of masses and mixing, right? They are not just random numbers, but they show a pattern. They are highly hierarchical, and therefore they hint to some kind of hidden structure that could reveal features of an underlying theory. The standard model can reproduce the observed structure of quarks and leptons through the Yukawa couplings, which contain even more free parameters than physical observables. However, the standard model provides only a successful parametrization of the flavor puzzle, but not a solution. And to solve the flavor puzzle, we must go beyond the standard model. And here enters a second aspect of the issue, which I call the flavor problem. And because the standard model flavor structure is very special. For instance, it predicts that processes with quark flavor transitions without neutral, without electric charge exchange are very much suppressed. Moreover, the standard model predicts that the same transition for leptons are essentially 0 because are proportional to neutrino masses. And finally, that the standard model predicts that CP violation processes are so very much suppressed because proportional to the product of all quark mixing angles. And these features of the standard models are very fragile and are likely to be broken in nearly any extension of the standard model, even those that superficially appear very innocuous deformation of the standard model. So just as an example, just take the very simple extension of the standard model with 2 Higgs doublets instead of 1, and generically, this leads to very large neutral current flavor violation at 3 levels. So the flavor problem is the statement that extensions of the standard model aiming at explaining the naturalness of the Higgs boson generically do not share the special flavor properties of the standard model and therefore fail to pass the experimental tests. And a typical example is low energy supersymmetry, which not only suffers from the flavor puzzle, like the standard model, because it cannot predict the Yukawa couplings, but also generically introduces a flavor problem. So the traditional approach to address the flavor problem is the use of global symmetry. And this seems an obvious strategy given the success of symmetry to explain all structures in particle physics from the old-fashioned eightfold way for mesons and baryons to the gauge group of the standard model. However, so far, all these attempts, at least in my opinion, had only a very limited success. So let me look at an interesting alternative approach, which is based on a 5-dimensional space with warp geometry and a curvature, which I call it K, limited by 2 branes at a distance pi r. So this is a slice of 5-dimensional anti-de Sitter space. And let's consider a free fermion propagating in this space. So in 5 dimensions, fermions are not chiral, but I can separate them in left and right components. And assuming separation of variables between the 4-dimensional coordinates, which I call it x, and the 5th-dimensional coordinate, which I call it y, each fermion component can be expanded in Kaluza-Klein modes of ever-increasing masses, which are labeled by the index n. Now, these functions f represent the profile of each Kaluza-Klein mode along the extra dimension and satisfy some the canonical normalization condition in curved space. And by imposing special conditions at the boundaries of space along the 5th dimension, I can eliminate one of the 2 chirality between the left and the right spinors. And this is how one can obtain a chiral theory in 4 dimensions out of a non-chiral theory in 5 dimensions. And the 5D Dirac equation then determines the profile F. Since I'm interested in the low energy effective theory, let me retain only the 0 mode, which satisfies this first order differential equation, where this parameter C is the mass of the non-chiral 5-dimensional fermion in units of the ADS curvature. So the solution of this equation critically depends on the parameter C. So if C is smaller than 2, the wave function is exponentially peaked on one of the 2 branes. If C is larger than 2, it is peaked on the opposite brane. So, and if C is precisely equal to 2, the wave function is flat along the extra dimensions. So let me now suppose that the Higgs boson is a 4-dimensional particle which is confined to live on a brane. And this situation provides a solution to the Higgs naturalness because the Higgs mass parameter now is exponentially redshifted with respect to the fundamental energy that determines the mass scales on the brane located at the origin. So let me compute now the Yukawa coupling of the theory. As an example here, I do it for the up quark, but of course I can do it for any Yukawa. So we start from a 5-dimensional interaction, and I put describe it a delta function for the Higgs, a delta function on the far brane, and this is where the Higgs live. And then using the zero mode profile for fermions, can then perform the integral over y, over the fifth coordinate, and I get that the effective 4-dimensional Yukawa coupling is given by an order 1 quantity times these psi factors, and 1 psi for each chiral component of the standard model fermions. So the psi parameter is exponentially suppressed if the corresponding parameter C is larger than 1/2, otherwise is a constant over the 1. So now you see how quarks and lepton masses, the hierarchies of these masses are naturally generated. The C parameter for left and right quarks are all roughly of order 1. So there are no hierarchies that are put in by hand. However, since the Yukawa couplings have an exponential dependence on the parameter C, large hierarchies are naturally generated out of order 1 quantities. So the pattern of Yukawa couplings is not the result of special input numbers, but is explained by a generic geography of quarks and leptons in the warped extra dimension. And this theoretical framework can potentially address both the Higgs naturalness and the flavor puzzle. At first sight, this setup may be interesting, but it's using ADS, extra-dimensional world, may seem a bit abstract and bizarre. But let me try to look at the theory from a completely different viewpoint. So a picture in a 2-dimensional representation is, it represents, it's a 2-dimensional representation of a 3-dimensional reality. So this is a painting by Seurat, and you see many people in the painting, and some are very big and some are very small. But your visual perception immediately tells you that the picture does not represent a world in which there are giants and dwarfs. All people, you expect that all people have roughly the same size in the real 3-dimensional space, but in the 2-dimensional representation, people near the observer have larger sizes than people far from the observer. So in the 2D projection, the distance along the 3rd dimension, that is depth, which is hidden, is instead replaced by size. And in the painting, the size of the characters carries the information about their position in 3D. And this is very familiar to you. Your brain immediately translates the information about size into information about position in the hidden 3rd dimension. Well, something like that happens also in certain quantum field theories, and the phenomenon is known as ADS-CFT correspondence. So there is a duality between a 5-dimensional theory with gravity in a warp space, and a 4-dimensional, strongly interacting conformal field theory. This is perfectly analogous to the equivalence between the 3-dimensional reality and a 2-dimensional picture in which size carries the information of distance in the in the hidden extra dimension. So in the ADS CFT correspondence, the position along the extra dimension is mapped into the energy scale of the four-dimensional strongly interacting field theory. So traveling along the extra dimension corresponds to the evolution of the renormalization group. And the boundaries of the slices of ADS space then correspond to infrared and ultraviolet cutoffs that break the full scale invariance. So let me analyze the generation of Yukawa interactions in the context of a four-dimensional strongly interacting theory, which is a phenomenon known as partial compositeness. So consider a sector made of elementary fields containing the three generations of quarks and leptons charged under the standard model gauge group, but without any Higgs sector. So this is a kind of a Higgsless standard model. And then consider a strongly interacting sector made of composite operators, generically parameterized by two quantities. Typical strong coupling, which I will call it G star, and a mass gap of the near conformal theory, which I call M star. Sort of simplifying the problem, and this M star, so it's a typical mass of the resonances. I mean, you can think of exactly the raw mass in the case of QCD. And the two sectors talk to each other in two ways. First, through the standard model gauge interactions, since the composite operators have gauge charges, and as a result, the standard model gauge bosons couple to some conserved current of composite operators with a coupling constant given by the ordinary gauge coupling constant. And then second, the two sectors talk to each other through mixings between elementary fermions and composite operators with couplings lambda, which are couplings typically of order 1. And these lambdas are not the Yukawa couplings, but they're progenitors and do not have any particular hierarchical structure. So at some high energy scale lambda, which defines the ultraviolet cutoff of the theory, the Lagrangian of the theory is described by the standard model kinetic terms without the Higgs, by a quasi-conformal invariant sector, and by a linear interaction between standard model gauge fields and the CFT current, and by a linear coupling between the standard model fermions and composite operators of the CFT, plus some other irrelevant interactions. And as you approach the scale, so at the compositeness scale M star, where you integrate out the resonances, the effective low energy theory contains the kinetic and potential terms for the Higgs, which complete the standard model, and which come in from the strong sector, but for some reason remain light, and the Yukawa interaction. For simplicity, I write here only the up Yukawa couplings, but the story is analogous for other couplings like I did before. So the Yukawa couplings is given by the product of the two corresponding lambdas evaluated at this scale M star at which resonances are integrated out. And then the strongly interacting sector is nearly scale invariant, and therefore the running of the coupling of lambda is determined by the scaling dimensions of the operator O. Therefore, the evolution of lambda is proportional to the ratio of mass scales to a power equal to the anomalous dimension. So this is an exponential when written in terms of RG logarithm. So as a result, the Yukawa couplings are given by order 1 coefficients times psi factors, which are order 1 when the anomalous dimensions are small, and therefore the fields are nearly free and elementary, and exponentially suppressed when the anomalous dimensions are large, and therefore the fields are mostly composite. Now you can see how the completely different perspective of a strongly interacting theory on one side and warp extra dimension on the other side give exactly the same result. And indeed, we can write down a dictionary to translate concepts from one language to the other. So moving along the extra dimension corresponds to the RG evolution of the strongly interacting theory. And the size of the extra dimension corresponds to the extent of the quasi-conformal running, which is given by the log of the ratio between the UV and the IR scale. And the localizing parameter C corresponds to the anomalous dimension gamma. Therefore, particles localized near the Higgs brane corresponds to states with sizable anomalous dimensions, which are effectively composite. On the other hand, particles localized far from the Higgs brane correspond to states with small anomalous dimensions, which are nearly free elementary fields. So using completely different viewpoints, we found that the Yukawa couplings must be hierarchical. And I'd say that this scheme not only explains why hierarchies are present, but it really makes them almost unavoidable, because Yukawas are exponentials of order 1 parameters, so necessarily they are there is some large hierarchy of small numbers. So under the 5D viewpoint, this is because of the geography in extra dimensions. And under the 4D viewpoint, this is because of anomalous dimensions generated by strong dynamics, but the results is identical. So if you find the one language is too abstract, well, use the other language. If you find that the strongly interacting language is not good enough to do calculations, well, you can do calculations in extra dimension. It really doesn't matter which description one chooses, even if there are advantages sometimes of using one or the other. So when you ask the question, so are Yukawa couplings hierarchical because of geography in extra dimensions or because of strong dynamics, or is what is real? Is this extra dimensions real, or is really the Higgs really a composite particle? Well, these questions are in a sense ill-posed because they are the same. They are two different descriptions of the same reality. So it's really like the painting in Paris in summer, and where you can interpret it as a three-dimensional reality or as a two-dimensional reality. So in conclusion, this scheme can address the naturalness problem and the flavor puzzle. But what about the flavor problem? Well, the strong sector violates subtle properties of the standard model, and therefore, unsurprisingly, it gives rise to effective four fermion and dipole interactions, which lead to strong constraints on the composite scales. And the strongest limit comes from the electron electric dipole moment, which sets a bound on m star of about 1,000 TeV, depends a little bit on how you define things. So these limits can be partly relaxed by making some assumptions on the flavor structure, but it's typically very difficult to bring m star low enough to make it compatible with a fully natural Higgs. Well, when I accepted this invitation to talk at this Congress, I was planning to show you a solution, because in collaboration with Kaustub Agashe, Riccardo Rattazzi, and Raman Sundrum, we are dealing with these issues, and we have made interesting progress in developing a theory that really addresses all these three issues simultaneously, three issues of fixed naturalness, flavor puzzle, and the flavor problem. However, unfortunately, I underestimated the time that it took to finish the project, so I'm not ready to show you the details. At the moment, all I can tell you is that I think that this direction really offers new possibilities for model building. So let me now switch to the second central issue of this talk, which is the origin of electroweak braking. So the situation with electroweak braking is analogous to the flavor puzzle, right? The standard model offers a perfect parameterization of the phenomenon, but is unable to give an explanation. So just like before, I was saying that Yukawa couplings can describe but not explain flavor. The Higgs potential can describe but not explain the origin of electroweak braking. It's very similar to the case of superconductivity. You have the Landau-Ginzburg theory, which gives a phenomenological description of the phenomenon, but you have to go to BCS to understand the microscopic theory. And the standard model tells us the how these phenomena, electroweak braking and generation of masses are generated, but you need to go beyond the standard model to address the whys. And at the core of the electroweak braking problem is the puzzle of fixed naturalness. The problem is well known. I will not repeat it here. In a quantum field theory, the quantum corrections push mass parameters to the maximum value allowed by symmetry. So naturalness then can be turned into a powerful tool to explore the properties of a theory beyond the boundaries of what has been tested experimentally, because it gives us information about the maximum energy up to which you can extrapolate the low energy description without running into this problem. The naturalness of the Higgs mass indicates the necessity to have new physics around the weak scale, and yet the LHC has not discovered any new phenomenon. And so this result had an enormous impact on the field. And so I think it's time to reconsider critically the hypotheses that go into naturalness to try to see and get hints on what should be the next step for our exploration. So the first hypothesis, hypothesis on which naturalness is based, is scale separation. So the whole framing of the problem of naturalness is based on the existence of multiple energy scales, well separated. If you don't have it, there's no problem because you can't even formulate it. So if you, for instance, take the standard model in isolation as a renormalizable theory, well, you don't have that problem unless you think about Landau pools. Simply because there are no scales to start. So the question then, are there any new energy scales above the weak scale? We don't know the answer, but I think we have very good reasons to believe that the most plausible answer is yes. I mean, the quantum gravity leads you to a scale, neutrino masses, the strong CP problem, inflation, gauge coupling unifications, flavor. They all provide indications that new heavy modes must exist. Of course, it's not indisputable evidence. So, for instance, this hypothesis was challenged by the idea of large extra dimension, which tried to bypass naturalness by postulating that there's no scale separation. All the scales are coincide with the weak scale. Or also the idea that of asymptotic safety in quantum gravity, that there is no need to modify the theory. So the lack of any mass scales about the weak scale, however, is not just a simple assumption. It's really a very ambitious assumption, because it requires, the moment you make it, it requires that you solve all problems of particle physics at once. So this is still an open possibility, but it's certainly very difficult, seems to me very difficult to believe that there are no energy scales above the weak scale. The second hypothesis is the validity of effective field theory. So the naturalness principle really relies heavily on the effective theory approach to quantum field theory, since it measures the sensitivity of heavy modes integrated out from the low energy theory. So you are, from the effective theory, you're trying to make a guess on what are the modes beyond the validity of the effective theory. So the question then, if you think that this was a weak point of naturalness, is that can effective field theory break down? And this is, of course, would be an absolutely revolutionary result, because for centuries, physics made progress exactly because all natural phenomena can be described layer by layer. So Newton didn't need to know about the atomic structure of matter to compute the orbit of the moon around the Earth, and Bohr could compute the atomic levels without knowing about the existence of quarks and leptons. So this is because you can separate phenomena scale by scale, and we've been accustomed. This is now sort of given for granted that this that it is possible to give consistent physical descriptions within a certain energy range without having full knowledge of physics at arbitrary short distance. That physics can be reabsorbed in some values of the parameters. But of course, it's not guaranteed that nature satisfies this EFT hypothesis. And this has been, it's always been the reason why we could make progress in physics, because progress in physics can proceed step by step without requiring simultaneous knowledge of physics at all scales. So the idea that there could be a significant interplay between phenomena short and long distance would be really a complete conceptual revolution of our understanding of physics, or what you mean by the physical description of reality. So renouncing to the principle of EFT sounds crazy, but there are some interesting indications that it may not be completely crazy. And we're used to think that high energy means short distance, because with higher and higher energies, we probe deeper and deeper into the structure of matter. But as you know, as you consider gravity, the story may change, because once the scattering energy exceeds the Planck scale, you form a black hole. And its horizon has the size of the Schwarzschild radius, which is proportional to the energy. And this hides the inner region of space to outside observer. And the bigger the energy, the bigger the Schwarzschild radius. So this means that as we increase the scattering energy, we get less and less information about short distance, exactly the opposite of the normal intuition. So in a sense, gravity could lead to some IR UV interplay. There is another indication that EFT may not catch the full physics story, even within the low energy domain, and this is given by the various swampland conjectures. And these conjectures, some of which are partly supported by theoretical evidence, state that not all theories that look perfectly consistent with the rules of symmetries at low energies are actually allowed to have a high energy completion that includes gravity. And it is said that these low energies theories live in the swampland because they're not part of the real theory landscape. Not all theories that are allowed by the usual rules of EFT, symmetry, and selection rules necessarily have a consistent UV completion in the context of quantum gravity. There could be restrictions in the IR that are completely inexplicable from a low energy point of view. Of course, this is not sufficient to say that there are IR UV connections, but it exposes some limitations of thinking only in terms of low energy theory. There is some information buried at short distances that trickles down and influences much larger distances. And this is an unusual perspective, and it really challenges EFT intuition. And showing a breakdown of EFT in particle physics would be revolutionary. It's so revolutionary that we don't even know how to do it, because it really required a theory with interplay between IR and UV, which sounds like you're breaking locality. But the idea is fascinating. There are some ongoing attempts based on modular invariance, magic zeros, quantum gravity conjecture, and so on. But I must say that I feel that we are still rather far from formulating our theory. I want to give you one example of a possible IR UV mixing for the cosmological constant. This example was given by Cohen, Kaplan, and Nelson. So consider a box of volume L cubed. And according to QFT, the number of degrees of freedom grows with the volume of the box. Therefore, the entropy of the QFT system must go like L cube, lambda cube, where lambda is a UV cutoff. However, the entropy cannot exceed the maximum entropy of the box, which is given by the Bekenstein black hole entropy. So this implies a bound that L must be smaller than MP maximum Planck mass squared divided by lambda cube. Therefore, you see that the IR, the size of the box, a cutoff, and L cannot be chosen independently of the UV cutoff lambda. There is some kind of IR UV interplay. And it's actually possible to derive even a stronger bound by arguing that states whose Schwarzschild radius is larger than the box make the system collapse. And therefore, the maximum energy states must have a Schwarzschild radius smaller than the size of the box. If you do the exercise, the algebra, you find that the bound on L now scales like m Planck divided by lambda squared, which is stronger than before. And curiously enough, if you use as a Hubble radius as your infrared cutoff, you find that the UV cutoff has to be smaller than 10 to the minus 3 eV, which is approximately the observed value of the cosmological constant. Now, don't misinterpret me. There's no solid base from this bound, but the reason why I'm showing is that it is interesting that, it's interesting that it predicts numerically the right value of the cosmological constant. But the most interesting part is that there is an interplay between infrared and UV cutoffs, and this can be crucial to make a physics prediction. So it illustrates that there are cases in which a simple effective theory analysis does not really catch the full physical content of the theory. But let me now comment on another aspect, which is the issue about the symmetries. I mean, in the construction of effective field theory, symmetry is crucial, right? Symmetry is what determines which interactions are allowed and which are not. And this is, I would elevate it to a symmetry paradigm because it's the way that particle physics theories have been constructed for at least the last 50 years with an incredible success. But although symmetry has been so successful and is definitely a cornerstone of physics, one may also see signs of decline in the concept of symmetry. The cosmological constant and the non-discovery of new physics at the LHC may be clues that the paradigm is running out of gas, because if you apply this argument based on symmetries, you have some predictions which are not then satisfied. So maybe the LHC, what is telling us is that it's not just a matter of adapting our models and making small adjusting the parameters, but it's really time to look for radically different paradigms. Then, according to one of the swampland conjectures, global symmetries are never exact and are necessarily violated by quantum gravity. And gauge symmetries are not really physical symmetries, since they act trivially on the Hilbert space. So a gauge transformation is not a transformation between different physical states, but only the expression of a redundancy in your parameterization. So maybe gauge symmetries are not as fundamental as we thought when we construct our models, but are only an emergent phenomenon. So there could be a mirage of a different reality that takes place at a much more fundamental level. And therefore, symmetry may not be sufficient to determine fully a low energy theory. Maybe there's something more to a low energy theory than simply the rules of symmetry. And while this is our intriguing clues, we still have to explore them and see where we can go and how far we can go. But let me now come to the hypothesis 3 that enters in the concept of naturalness, which is the fact that infrared free parameters must be calculable quantities in the UV completion. This is often not appreciated, and this is often the center of some claims that you can solve the naturalness problem without adding new physics, because it is really a central hypothesis of the naturalness principle. If the Higgs is what it is as an input, then there's no problem, there's nothing to explain. But whenever we formulate the question about naturalness of the Higgs, we are tacitly assuming that the Higgs mass is a calculable quantity within a certain fundamental theory, and we want to extract information on that fundamental theory. So, as an example, supersymmetry. In supersymmetry, the Higgs mass is calculable and is given by a combination of mass parameters that break supersymmetries and those that break chiral symmetry. And the story is the same for the composite Higgs. The Higgs mass is a loop factor below the mass scale of new resonances. And when the Higgs mass has a precise expressions in terms of new physics, then naturalness provides information about the size of the UV parameters. If you don't have these relations, there's nothing you can derive. There is an interesting way in which hypothesis 3 could break down. And this is the case in which IR parameters do not correspond to a unique expression in terms of UV quantities, but they are functions of some fields whose values vary during the cosmological history or throughout a complex vacuum structure realized in the universe. So this point of view is a profound paradigm change with respect to the usual approach based on symmetries. It's really a radical changing perspective. However, it is deeply connected with the physical theories of the cosmos and gives the physical, and it's attached to a physical reality that can lead to precise prediction. It's actually something very familiar to most particle physicists. Take the case of the axion, right? In the case of the axion, the starting point is the observation that there is a standard model parameter that should be of order 1 according to EFT, but then you measure the neutron EDM, and that tells you that it must be smaller than 10 to the minus 10. To deal with the paradox, the idea is to promote the standard model parameters to a dynamical field, which is the axion. And then during the cosmological history, this axion explores the full possibility of the fields, and then there will be some dynamical reasons why the vacuum is chosen. And recently, this logic has been extended to various theories, which I think have some interesting features, although I must say, I'm the author of some of them, so I can be honest, that there's not a single proposal that is fully satisfactory. Although some of the elements I believe could be interesting for future work. So let me get to my conclusion, trying to summarize what is the message that I try to pass. So first message is that the LHC is really an extraordinary scientific project. It has accomplished a program of precision measurements that could have not even anticipated at the time that the LHC has started. And this was possible only because of a successful interplay between very different sectors. Exceptional accelerator performances, excellent detector resolution, high performance computing, high order theoretical calculations that can give precise prediction on the background, and various technological development. We should really keep it in mind when we're thinking about the future. And also the breadth of the scientific program has been remarkable and even went beyond what was expected before. However, we should also say that the success of the experimental program has created a puzzling situation from the theoretical point of view, because we expected that the LHC would give us decisive hints to solve the issue of Higgs naturalness, but despite much experimental and theoretical progress, the origin of electroweak braking and the flavor structure, which are the topics that I discussed today, remain still unresolved mysteries. And many of the hypotheses made before the LHC have not been confirmed experimentally. And so the results of the LHC has really forced us to reconsider these questions under a different light. They have transformed our ideas, and now we are facing the alternative. One possibility is that the traditional approach based on the logic of symmetry was essentially correct, but for reasons that we still not understand, there is a slight separation between the weak scale and the new physics. In that case, well, we should explore further with higher energies, and maybe we're going to find something. The second option is that the solution of Higgs naturalness comes from structure that were not even imagined before, and this should lead to a profound paradigm change, and this could turn out to be the true revolutionary legacy of the LHC. The mysteries of the electroweak braking and flavor are at the core of the high energy program, and therefore they must be further pursued if we wish to advance along this path of fundamental knowledge. And today, high energy colliders are our only means for a systematic exploration of nature at small distances. They are an indispensable tool for investigating the inner structure of matter and uncovering some of the universe's deepest mysteries. So here in China, the CPC project has the ambition to continue this exploration, providing a marvelous opportunity to address some of humanity's most fundamental questions about nature. And in Europe, a similar project is being considered, and this will be discussed by my colleague Christophe Grosjean. International cooperation is essential for our work as scientists. So more than ever, during these times of conflict between nations, it is vital for scientists from around the world to come together. We must demonstrate the immense value of human understanding across borders and advocate for international collaboration in the name of peace and progress. 谢谢。
Thank you very much. Any questions?
Thank you very much, Gian. I like to talk a lot. The first part you were discussing, explaining the flavor paradigm, also the new physics flavor problem in extra dimensions or a strongly composite. Have you considered what are your predictions of applying that to the dark matter problem, where in principle we have no indication of the scale and its connection?
Correct. So yes, I mean, in our model, of course, when you construct a model of particle physics, you can never forget. So let me just say that you can do it. It is possible because there could be some relics in this strongly interacting sector. If you do, you can. Of course, there are strong constraints because there could be states which are neutral and stable, and the energy scale, the mass scale of those states, when you try to solve flavor and so on, so you determine roughly that scale, turns out to be good since they are strongly interacting. You want a relatively high scale, so you are in the correct ballpark. Then, however, now with the limits that exist, these states cannot be simply neutral, but be fully neutral under also electroweak. And I have no idea how to predict the spectrum, so I can only put it as an assumption. So let me say in short, yes, it's compatible with the possibility of dark matter, but it's not that you have a clear prediction about its cross-section and so on. And you may also run into issues about having something which will be extremely difficult then to see it experimentally.
Yeah, John, thanks much for the very nice talk, as always. So I have a similar question along this line in the flavor sector, but much less ambitious than going to the dark matter. So you cast this into this nice picture between the three-dimensional and the two-dimensional and so on and so forth. And you get into this, you cover the couplings in terms of your anomalous dimension.
Right.
Do you expect that you will be able to predict the anomalous dimensions to get everything right with the fewer parameters?
Right. That is, the answer is no, of course. But let me just say, this is the limitation of the approach of partial composites. And this is a difference with respect to, say, flavor symmetries. In flavor symmetry, you also have the ambition of predicting exactly some relation, mass relation, and so on. Within the system, inherently, when you go to a strongly interacting sector, you don't know how to deal with that, and so it will never be possible. This is why I was emphasizing that one quotation mark prediction is that Yukawas have to be higher. And this is sort of, if they weren't hierarchical, this whole program would not work because it's very difficult. I mean, you have to tune all the anomalous dimension to be very, very, very equal, and that is difficult. So the only nice feature is that tells you, look, you should find it hierarchical. But when you go, sorry, but don't worry, don't worry.
rush.
If it is for me, then you can pass me the phone. But unfortunately, there's no way. The idea would be that maybe one day we'll have you can construct precisely the sector and you can have more information. But
So I really hope to hear your comment. Let me make a statement and you comment on it. So far, this is a good model. There are many other models such as Forgan-Nelson and so on and so forth. My statement is that I have never seen any model to be able to predict it's more than fewer parameters than your cover couplings. At the very end, you always come back to fit your cover couplings and to fit this minimal flavor violation. I don't see any progress. I don't see the fundamental progress along this road. You fit the parameters.
So look, this is, for me, this issue about flavor is the most embarrassing aspect in particle physics, right? Because, we are all obsessed with understanding why the mass of the Higgs is what it is, one parameter. And then we have this large number of parameters which all appear in the Yukawas, and we all say, okay, So definitely is the biggest problem, and we've been facing it for so many years. Remember that Weinberg one said, okay, I'm going to spend the summer, the full summer, and I'm going to solve the problem. Okay, of course, he's, well, he failed, okay? So a full summer of Weinberg corresponds, if you were there at the talk of Uguri, he was trying to compare time scales. I don't know how much time that corresponds in a normal human endeavor. So it is a problem which is clearly very important, I would say central for particle physics, but obviously very, very difficult. So at that stage, any small progress for me is progress. Even if of course, if I could come up here with a model in which I tell you, now I can tell you all masses with, precision of 10%, all mixing angle, great. But obviously we're not at that stage. So it is worth thinking of what are the structures, even if you're not as ambitious of getting all the numbers, but what are the try to, be more systematic of what we've been so far. In the case of naturalness, we've explored, the whole community has explored the problem with, so much that we know how to map it fully, what could be the solution, what kind of dynamics. And of course, you never cover the whole thing, but we have very good ideas. The case of flavor, a lot less has been done, in spite of being how big the problem. And therefore, I think that, the idea of Frogan-Nielsen, flavor symmetry is a possibility. But my intuition says that if we had a symmetry that would do it, by now we would have found it. We are good enough with symmetry that we can play with, and no possibility. So moving more towards dynamics, that maybe it's the dynamics at the end is the solution. To me, seems an interesting path. True, the advances that you can make, at least at this stage, are fairly limited. But once you try to play the game of saying, okay, I want to have a theory that understand what I was calling the flavor puzzle. I mean, deriving this parameter, and at the same time not encounter flavor problem, you're very much constrained. So already finding examples of theories that could do that, for me, is progress. Not an enormous progress, but I would consider a progress. So if I take two examples, which you have supersymmetry and another with composite Higgs. So you said that in this theories, the Higgs mass can be predicted from the scale. Yes. Okay, suppose that, okay, it did grow nicely, but suppose it would, then you would rediscover the similar problem with the scale of supersymmetry breaking and with the scale of composite, because all these theories should be embedded into gravity. And then the question of computability of the scale from gravity reappears again. So conceptually, so let me answer. Now, I think I got the question. So, of course, you always will have one problem, okay? But you have made a huge step forward, because the problem of the Higgs is that it's an elementary scalar and then suffer naturalness. If you have issues, okay, as n minus one people believe, and then, but then the scale of supersymmetry, of course, you want to understand the number, but you don't necessarily have a problem of naturalness there. You know, for that scale could arise from some Giudice condensation and so on. So in the same way as you don't worry in QCD, why is it natural to have the scale of QCD what it is? You can have exactly the same phenomenon. So you have resolved the technical aspect of naturalness. The technical, I mean, the issue about quantum corrections, but you still would have an input to define. But again, it's similar to that. Is one step further. I don't think that we will ever find the final theory, everything is solved. The idea of going in physics is making progress. And I must say that while the problem that I was bringing up, it's valid, and so you may call that a small step. But the moment that I would discover supersymmetry, and I find that the theory now becomes natural all the way to the Planck, the unification scale, is a big step in my view. Perfectly well. This is why I think I was very glad when I saw you. I didn't expect you in the audience, but because I think that sentence, and I even I stressed it a little bit because it's really for you. See, as I was saying, the naturalness problem exists only in a theory in which you have where the Higgs mass is computable in terms of something. Okay, so then the theory tells you information about some physical parameters, and you can compute quantum corrections which are finite within that theory. Okay, which is also an effective theory if you wish at a larger scale. So those corrections are perfectly computable, and they will be proportional to, say, the square masses or whatever. I don't know. Yeah, if you. Yeah. I say that you can say it, not in general, but within the class of theories in which the Higgs mass has a calculable expression in terms of physical parameters of the UV completion. So this is the class of theory I'm considering. If you go beyond that, I think the problem then, of course, this does not apply, but I think it's a little bit vague then, because okay, then.
Okay, let's move on. Yeah, let's
Never
move
resolve
the
it.
discussion.
Yeah, this is going to be a famous, very long discussion, but I will hopefully have a shorter question so that yeah. So I think there are lots of effort in the past. Some of them you alluded to is to even just address the little hierarchy problem of the flavor little hierarchy. flavor part involving flavor symmetries and so on. And in your view, what's the most unsatisfactory thing with all these attempts that people try to lower the 1000p scale down to?
Right. I mean, if you had asked me, before the LHC, I would have an answer. I think now we are in a state in which I'm not ready to make even a bet of what is. I think at the moment we are in this stage of broad exploration, and I would not be ready to rank what is the most promising direction in which to deal with this thing. For instance, in this particular model that structure that we are constructing, we've been changing our mind on how to do it several times, which shows where we don't have a predefined opinion on how to resolve these issues of the small scale. Very often because the resolution of, let's call it the little hierarchy of flavor, very often is not something that descends from principles, but really descends on specific model features that you add the right article, then you change the structure. So I don't think there is a general answer or general strategy that you should follow. You should face the problem in your particular structure and then see what are how you can modify or adjust your model to explain it. Very unsatisfactory situation, but I think that's what it is.
Okay, great. Thanks to Professor Giudice for the very nice talk. Beautiful.